Tutorial 6, Chapter 6. We're going to look at graphical models for organic molecules from the Spartan Spectrum Properties database. So we won't be running calculations, but we'll retrieve previously calculated structures from the database, and then we'll use Spartan to display different graphical models. Similar to the last tutorial, we'll build examples that we've looked at before. So we'll look at nicotine, I think also an N-dimethyl-aniline, and then androsterone. And we'll look at 3 different surfaces. We'll look at the electrostatic potential map, we'll look at the local ionization potential map, and then we'll look at the LUMO map. So first up, we'll look at nicotine. Okay, so nicotine is over here on the left-hand side. Let's sketch this quickly in 2D. You may remember this from earlier, but let's see, double click and we'll put a benzene ring. Let's just drag out and we'll insert a 5-member ring over here. So this is phenylcyclopentane, and then let's go and grab nitrogen. Double click to replace, make that pyridine. Let's make this a pyrrolidine and drag down. Okay, and then just to point out, this attachment point at the 5-member ring is a chiral center. And what we want is essentially this pointing up. So let's make that up. Okay, so in an upwards direction, so above the 6-member ring, this is nicotine. Okay, and we'll do go into view mode. So let's just move to 3D. Zoom in. Let's replace this as we've done in the past from the Spectrum Properties database in the lower right corner. So you click on the name nicotine, click replace, and then we have an optimized structure. We've done this. Let's just take a quick diversion. Let's just look at the output summary. Okay, so this is done with Omega B97 XD. This is the 61G star geometry. Okay, so calculation completed, retrieved from the database, and then let's just go into the the surfaces dialog and request an electrostatic potential map. Okay, so you can request surfaces in a few different places. Surfaces are available under the setup menu surfaces, also typically the display menu surfaces, and then it should be a permanent icon over here. It looks like an electrostatic potential map near the spectra icon. So you click on that, and that'll drop you down into the surfaces dialog. Okay, in the lower left, there's a set of sort of basic surfaces that are available, and to the right of that, there's a button for more surfaces that allows you to do some customization. So let's just click on the Add button in the lower left, and the 4th entry down, the electrostatic potential map. Let's take a look at the electrostatic potential map. All right, so this will compute on the fly, takes a few seconds. Medium resolution is the default. You can increase that under more surfaces. You can change the resolution to higher if you like. Anyway, it took a few seconds. The job's completed. Let me turn that off again for just a sec, just to remind people. So we sort of have two kind of hot spots. We've got the nitrogen in the ring, in the 6-member ring, where we've got lone pairs, and then also the nitrogen in the pyrrolidine ring. So there's an excess of electrons in both of those, or at least electrons in both of those places, as the electrostatic potential map shows. If you can imagine a point positive charge out here at infinity approaching the electron density surface, we're colored red where we're attracted, and so we're attracted in both over the pyrrolidine and then also the pyrimidine nitrogen. Okay, and it's a little bit hard to sort of place things underneath the hood, so let's go ahead and do the following. If you click on the actual map, that sort of selects it, that points it, makes Spartan sort of aware of it, and then go to the properties dialog, you'll have the surface properties. So if you click off screen, sort of something in the background, with nothing selected, the properties refers to the molecule, and when you click on the surface, it now refers to the surface properties. Okay, so we see this is an electrostatic potential map. We see the surface range, which is -200 to +200 kilojoules, and we see these sort of 2 hot spots. There are 2 places that we can modify the view here. We can either do that from within the surface properties or down here in the lower right of the actual Spartan interface. There's an option to sort of change the display style. So let's go ahead and make that just transparent for now so we can sort of see underneath. And you can see that the larger red spot is sort of over the pyrimidine. Let's quantify that. So we can see it's red rather than orange, and it's a little bit bigger. It's easier, I guess, to see in solid. But let's go ahead and make a measurement. From the surface properties dialog, in the sort of lower right-hand corner, you'll see a display section. Check the box that says legend. That'll put a little legend map up on screen. If you click on that to select it, you can use the right mouse to move it around if you want to. But basically, this is a sort of a key to let us know. So if I touch over here in this red area right around the nitrogen in the pyrimidine ring, we see I'm down at about, actually almost at the max, at minus 198 kilojoules of attraction. And then over here on the pyrrolidine nitrogen, let's just take a look underneath the... So on the pyrrolidine nitrogen, if we go and take a measurement, we see that we're at what? Something like minus 129 or minus 120, somewhere around there. Okay, so still definitely attractive to a positive charge, but not as attractive as this hot spot. Okay, so charge distribution using the electrostatic potential map. Now let's take a look at N,N-dimethyl-aniline, something that we've built before. Okay, we can close this example and let's go take a look at the next tutorial. Okay, so N,N-dimethyl-aniline, we're going to look at the local ionization potential map. So we built this before. Let's just do this again quickly in 2D. Just grab benzene, double click, grab the nitrogen, and sort of drag out from the carbon, and then just put a couple of methyl groups on the nitrogen. Okay, so N,N-dimethyl-aniline, we clean that up. We'll go into 3D. Let's go and retrieve this from the SSPD in the lower right corner, just to remind everyone. All right, so once it's retrieved from the SSPD, we've calculated its geometry at an omega B97 XD631G star geometry. So at a density functional model with a generally decent basis set for geometry. Okay, so we have the wave function available so we can generate graphics. So let's go ahead and go to the surfaces dialog. I'm going to grab that from the toolbar, but you can get there from the display or setup menu as well. Let's go to add, and in this case we're going to do the local ionization potential map. And just a quick word about this. So the electrostatic potential map we looked at in the last example is really a charge distribution map, but the local ionization potential map, it asks a similar question, but it's subtly different. It's how easy is it to ionize? So how easy is it to pull electrons from an area? And we'll basically, it's a different range. It always requires energy, so it's a positive value, and we use electron volts just by convention. So let's take a look at that. It'll compute quickly. And let me make a comment. We'll close the surfaces dialog and go to the properties dialog. By default, well, this is the molecule properties. So click on the surface to convert the properties dialog to the surface properties, and you can see that in the upper left. So by default, the property range, what we try to guess, it's 5 to 15 electron volts. But you can see right underneath that is actually the absolute range calculated for this system. So at the low end, it's 10, and at the high end, it's a little over 17. Okay, so let's do the following. I'm just going to click this button that says Reset Min Max. So we're going to, instead of using the 5 to 15 electron volt range, we're going to use the min max for the molecule, which is 10.6 to 17. Okay, I just mentioned it's a more sensitive probe, so when you look at the local ionization potential map, you may need to come in and modify the range a little bit to hone in on the area that you want to focus on. So for example, in our case, what we were looking for is, hey, where is it easy to remove electrons? Okay, so this happens to be at the amine, and this makes sense, right? That the electrons, the lone pairs over the amine. So let's take, actually, let me go back here and we'll turn off the solid and we'll make it transparent just so you can see over the amine. But then also if you go to the ring, it's sort of in the ortho and the para positions, okay? And the same is true if we flip sides. So we're accessible. The amine is accessible on this side. It's pyramidal. So it's sort of here. Let's turn the surface off for a moment so we can see underneath. Okay, so when we rotate on one side, we have interference from these two protons, and then on the other side, they're sort of the protons are spread out, so it's more accessible. So it's accessible on one face and not on the other. Okay, so on the inaccessible side, also ortho and para, we see it's easier to remove electrons from these locations. Okay, completely consistent with the chemistry of dimethylanilide. Okay, now let's look at the next example, which I think for some reason we're going to do androsterone again, which is a little bit difficult to build, but I may build it in advance. We'll see. And that will be again available from the activities menu, tutorials, and then we're on tutorial number 6. All right, and the next example is indeed androsterone, and we're going to look at the lowest unoccupied molecular orbital and the lowest unoccupied molecular orbital map. So the idea is essentially to use that as an indicator for nucleophilicity. So if I were a nucleophile approaching this with excess electrons and asking the question, so where am I likely to interact? I'd probably like to put those electrons into an unoccupied orbital. So we'll look at the lowest energy unoccupied molecular orbital for androsterone. And we'll just close the existing file quickly. And let me just build this in 2D or sketch it really quickly. So give me a sec here. Okay. A little bit boring to watch this, so I apologize, but maybe could have used a different example. I guess the good news is if you followed along, you built this once already, so it should be pretty familiar to you. I think the one goes up here, and then there's these methyls to deal with. Okay, so this is in principle androsterone. Okay. Yes, androsterone in the lower right corner, so we'll click on the view mode to get that into the 3D space, and then let's do our retrieve function from the SSPD. So we'll replace this with a calculated and optimized geometry. And then let's just look at this sort of from the side. So sideways, you can sort of see there's two faces. We're talking about interaction with the carbonyl group at this end with regard to a nucleophilic attack. So we can either do that. We can either approach that carbonyl from the side with the two methyls, or which seems a little bit crowded, or to the side without those, which seems less crowded. So let's see what the molecular orbital looks like, and we'll see. Okay, so here's the side without the methyls. Okay, so we'll go to the surfaces dialog, and we could grab that from the toolbar up here. And let's request two surfaces. First, let's add the LUMO, so the lowest unoccupied molecular orbital. That's a fast calculation. And we see that it is indeed sort of centered around the carbonyl functionality. And there are sort of two faces. Okay, and then now let's take a look at that LUMO, and let's ask a different question. Let's say, okay, well, once I talk about the density, so we're going to map the LUMO onto the density. The density is sort of how close can I get? So we'll ask the question, okay, how close can I get? And then where is the LUMO? Where's the unoccupied orbital? And let's take a look. Okay, so how close can I get is the surface, and then colored blue is at the maximum level is the LUMO. So that's on the face away from the two methyl groups. So here, let's just turn this off for a moment so you can see it. So there is definitely there is a sort of light blue area right here, but we would probably say based on this dark blue availability of the LUMO that more is accessible on this side. So this is the more likely face. And so, I mean, it's good that molecular orbital sort of agrees with what you would typically just think from your intuition with regard to steric crowding. Okay, so that was the last example for the graphical models, at least at this point, and now we'll turn things over to the next section, which was, I think we're going to start doing calculations, so let's see. Yeah, spectra properties and graphical models from calculations. So this will be, I think, tutorial 7, and we'll begin that shortly.